Hey everyone, welcome back to TryHackMe's Advent of Cyber 2. I'm Dark, and today we're going to be doing Day 17, Reverse Elf Nearing. Now, this is going to be the first of 2 days on reverse engineering. If this is something that you haven't done before, don't panic. Thinking of Hitchhiker's Guide to the Galaxy. Always make sure that you have your towel. No, I digress. This is something that isn't as scary as it seems at first glance. What we're going to be doing with reverse engineering at most becomes about as complicated as basic math. So as long as you're comfortable with addition and subtraction, trust me, you can get through this. You'll just have to bear with me. This is one of those topics that makes a lot more sense in practice rather than in the theory of it. So once we start talking about things, these are fairly basic topics. This is a very nice introduction into actually being able to start to understand how assembly code functions. And it'll be, trust me, it won't be too overwhelming once we actually get into it. So don't panic too much. We'll get through it together. And this will be a nice little refresher for me because it's been a while since I've personally touched any assembly, and I have a Ghidra book sitting and waiting for me. If you're familiar with the one from No Search Press, that's one of my next reading projects. So fun things. We're going to go ahead and do day 17, and with that being said, we'll go ahead and dive right in. Now, with getting started, I've gone ahead and I've already deployed the attack box, and then the box attached to this task. I believe we're just SSHing into the box attached to this, so this is something that you can pretty easily do on your own machine. You don't need anything too crazy for this, but we'll go ahead and dive right in. So the story. McSkitty has never really touched low-level languages. This is something that they must learn in their quest to defeat the Christmas monster. Introduction to x86-64 assembly. Computers execute machine code, which is encoded as bytes to carry out tasks on a computer. Since different computers have different processors, the machine code executed on these computers is specific to the processor. In this case, we'll be looking at the Intel x86-64 instruction set architecture, which is the most commonly found today. Intel computers are super common, while the market space is shifting back to be a little bit more mixed, especially with Apple having recently released I think the M1 chip. That has a different set of instructions for it. Intel has a dominant market share, and they have for the longest time, especially within the business sector. So that's why for a lot of things within assembly code and reverse engineering, we just use the Intel instructions for that. It's not very different from other instruction sets, and by and large, most other CPUs are not that far off. Machine code is usually represented by a more readable form of the code called assembly code. So you have machine code, which is very, very low level, and then we have assembly code that's right above that. The machine is this machine code is usually produced by a compiler, which takes the source code of a file and after going through some intermediate stages, produces machine code that can be executed by a computer. Without going into too much detail, Intel first started out by creating a 16-bit instruction set, followed by a 32-bit, after which they finally created the 64-bit instruction set, which is what we use today. We'll probably eventually have a 128-bit instruction set. However, the 64-bit instruction set is very, very quick. And it'll probably be a while until we get a new one. All these instruction sets have been created for backwards compatibility, so code compiled for 32-bit architecture will run on 64-bit machines. This is why you can run older games very easily on Windows. It's actually the main reason it works. The instructions are already there, and it's very easy for Windows to have a compatibility mode that just handles all this for you automatically in the background. As mentioned earlier, before an executable file is produced, the source code is compiled into assembly.s files, after which the assembler converts it into an object program.o files, and operations with a linker finally making it executable. So we use a linker to we're connecting the dots there between the actual code and what the code needs to do. I won't go too far into that just because it's something that gets into a little bit of a finer level than even I'm comfortable with at this point, but it gives you a general idea of it's just a process that we We start from our high level code and then we just transform it however we need to make the CPU run it. And anyways, you will probably not be doing this by hand pretty much ever, because compilers just do it for you. You can do different sites. There are different sites that allow you to see how different compilers will end up producing the assembly code from what you've created, but that's typically for practice at that point. The best way to start explaining assembly is by diving in. We'll be using Radar 2 to do this. Radar 2 is a framework for reverse engineering and analyzing binaries. It can be used to disassemble binaries, which is translating machine code back to assembly, which is actually readable, and debug said binaries by allowing a user to step through the execution and view the state of the program. This just means, for those of you that have not done any debugging, we can set pausing points so the program will just halt. Nothing will move, nothing will run, it just sits there and lets us look at what's going on. Luckily for us, everything we need has been provided to you via an instance that you can deploy and log into. So we've gone ahead and deployed this. In this case, I'm going to go ahead and open up my terminal, make a note of the box that I'm going to be logging into. So we'll go ahead and echo that in. Your IP will likely be different than mine, so make sure that you write down yours at this case. Make sure I did that correctly. There we go. And then we have our username and password. We can go ahead and SSH into that now. We'll go ahead and trust that, and then advent of cyber. And this is one of the days that I would recommend. If you want a good instance when you can walk through it with me, I recommend doing so for this day, and then pausing the video, going back and trying it yourself. Trying this a couple times is definitely worthwhile, as this is all practice to get this down. Let's proceed to run through how Radar 2 works exactly. Although you shouldn't do this if the program is unknown, it is safe for us to execute to see what should be happening like so. Translating that, don't run anything you don't trust or don't trust the source of 100%. You shouldn't be downloading random binaries off the internet, because that's a great way to get viruses and just to hose yourself over. So in this specific case, we trust this program because it's coming from TryHackMe. So what we can do is, let's see what we have here. It looks like we have a challenge 1 and a file 1. And in this case, we can run, let's see, those are not directories, they're just executables. We'll run file 1, and we can see the value of A is 4, the value of B is 5, and the value of C is 9 Elf McEager at TBFC. Okay, I think it's just 9. The C is 9 in that case. This is just leftovers from my terminal prompt. So here we can see that it's running. It looks like that screenshot's just a little bit clipped off, but I recommend just taking a look at this. The above program shows that there are 3 variables, A, B, and C, where C is the sum of A and B, so we have 4 plus 5 equals 9. Time to see what's happening under the hood. Run the command R2-D, putting it in debug mode, and then the file. So we'll go ahead and clear this. R2-D, and then file 1. We'll give it a moment. There we go. This will open the binary in debugging mode. Once the binary is open, one of the first things we are to do is ask Radar 2 to analyze the program. And this can be done by simply typing in AA. And that's going to go through and analyze all of the flags and various things throughout the program. I do not have a comprehensive list of everything that's analyzing, as, like I said, this is a little bit outside of my personal wheelhouse, but we're not going in too far of depth. All you need to know is this is going through and it's actually seeing what the structure of the program is, what the memory space actually looks like, which is the most common analysis command. It analyzes all the symbols and entry points in the executable. There we go. The analysis in this case involves extracting function names, flow control information, and much more. So we're looking for functions, we're looking for if statements or while loops and other different flow control information, and then anything else that might be useful. R2 instructions are usually based on a single character, so it is easy to get more information about the commands. So for example, for general help, we can run, and it looks like this is still thinking. We can just press a question mark. If we want to, for example, find out more information about a specific feature, we do the first letter of that command and then the question mark, and that's going to tell us about all the analyze commands. We'll let this do its thing. If it ends up freezing, I will just transfer this back over to the attack box, or I'll use my Kali box to make it run a little bit better. Computer says done. Once the analysis is complete, you would want to know where to start analyzing from. Most programs have an entry point defined as main. To find a list of the functions, run AFL. So we're given this just a moment. Looks like it's going to go ahead and continue analyzing. I am going to pause the recording for now, and once we are back, this will be done analyzing the file. All right, and we're back. That took, I think, roughly 10 minutes for me, so I've gone ahead and I have transferred them back as well to my host machine. Let me go ahead and pull that up so I can do further analysis on that as well. I am going to just leave that on the background in case we need it. This machine will likely see boost before the time that you guys get this. Radar 2 is a somewhat intensive program, so sometimes it can take a little while. That being said, expect it to be a little bit faster for you, but you'll just need a little bit of patience for that step. All right, computer says done. We can go ahead and we're going to get a function list. So analyze function list, AFL. We'll go ahead and let that run super quick. It's going to give us all of our functions here. And if we scroll up, I'll go ahead and minimize this one for now. We can see we should have a main function that is going to be our entry point. It's a lot of functions. This is the case where I'd recommend piping this into, yeah, we're going to pipe this into less. Let's see. So here we can see we have an entry point there, and we'll see if it gives us our main function. There we go. sim.main. That's what we're looking for. And we have our memory address there, which I'm going to go ahead and copy, as we are likely going to need that here in a moment. Note that the memory addresses may be different on your computer, so just be aware of that. Especially if you transfer these back, a lot of times your memory offset can be very different. So we've got that up here in the picture as well. As in here, there actually is a function at main. Let's examine the assembly code at main, or assembly code at main, by running the command pdf at main. We'll go ahead and do that with pdf at main. And there we go. We can see that we have our disassembled code there. Not super long as well. Where pdf means print disassembly function. Doing so will give us the following view, which we can see over on the right, which is a little bit bigger. And we can see a picture of that here as well. All right. Doing so will give us the following view. Yep, I had to pause that there for a second. We're getting the memory boosted on this VM to make it significantly faster. Register me this, register me that. The core of assembly language involves using registers to do the following: transfer data between memory and the register, and vice versa, perform arithmetic functions on registers and data, transfer control to other parts of the program. Since the architecture is x86, the registers are 64-bit, and Intel has 16 registers, which we can see down there. Looks like there's a small typo there. And so typically, registers, think of them as buckets or folders. We can put things into them. I don't believe we can transfer from... there are specific rules for where you can copy memory to, or copy data to and from. And the registers are just nice little folders that we can throw data into for doing functions. And we can store quite a bit of data in them because the registers are 64-bit in this specific case. So the initial data type, we have a nice little chart down here for the suffixes and then the size in bytes, so how much data is actually there. Here we can see a byte, which is prefaced by B, is just 1 byte. W is going to be word, which is 2 bytes. We have a double word, which is L. That is 4 bytes. As you might have guessed, it's 2 words. We have a quad, which is going to be 4 words, which is going to be 8. Single precision, which is represented by S, is going to be 8. And then double precision, which is again represented by L, same as double word, which is 4 bytes. When dealing with memory manipulation using registers, there are other cases to be considered. So we have the RB-RI equals the memory location RB plus RI. We have D-RB-RI equals memory location RB plus RI plus D. And then we have RB-RI-S, which is the memory location RB plus S times RI. And then D-RB-RI-S, which is RB plus S times RI plus D. So just keep this in mind. This is something that we're going to revisit, and this is something that makes significantly more sense in practice. It's probably clear as mud right now. So read the instructions. Some other important instructions are LEAQ source destination. This instruction sets the destination to the address denoted by the expression in the source. So note that the source is always going to be first in here, and destination is going to be the second one. It is a reading left to right in that specific case. We have add, which means the destination equals the source plus the destination. We're adding in to the bucket that is going to be our destination. Subtract or sub q, which is going to be the same as add q, but we're subtracting. There is imul, which is the multiplication function, where we have our destination equals the destination times source. Sal q, which is going to be the destination equals less than source, where less than is the left bit shifting operator, and then we have the right bit shifting operator. We have xorg q. You don't necessarily need to know these both, by the way. We're talking about just generally the full list of functions here. We have the xorg q, which is going to be xoring the functions, another mathematical function that we can perform on this. This is very common in cryptography. We have the and q, which is going to be our and function, and then we have or q, which is going to be our or function. This is something that you'll be familiar from with doing the Python days. Now let's actually walk through the assembly code and see what the instructions mean when combined. So the first line, starting with sim.main, indicates that we're looking at the main function. So we can see that up here, which is the sim.main. I'll scroll up to it over here on the side so it's a little bit easier to see. Function right here, sim.main, and then we have the sim.main, and it looks like we have some variables defined right away. The next three lines are used to represent the variables stored within the function. These three right here, you can see them up here in the picture too. The second column indicates that they are integers right here, so variable. All three of our integers, and then we have, it looks like the spacing requirements for these integers. The third column specifies the name that RT uses to define them, and the fourth column shows the actual memory location. There we go. So we have the name here, so local char, local 8 char, local 4H, and then we have the memory location that they're actually at there. Note that these are going to be relative to the RBP. This is the base pointer, so this starts at the bottom of the actual memory structure, if I remember correctly, and because we're working within a space that memory is all relative, from usually your base pointer, we have this minus relative space that we're defining how far it is from that fixed point that we know within the memory function. Think of it this way, everything's nebulous. Imagine you're swimming in a giant swimming pool and there is a buoy in the middle of it, or you're in the ocean rather. The ocean's really, really big, and so is computer memory. It used to not be as big. We have a lot of memory in modern computers, especially modern servers can have even terabytes of memory. It is easier to define things in that big space of memory as a relative location from a fixed point. In that case, it'd be the buoy, and say you have a person that is 5 feet from the buoy and then someone else that is 20 feet from the buoy. It's much, much easier to define it in that specific way. So think of it that way. We're in the sea of memory and we're defining things from a relative point. The first three instructions are used to allocate space on the stack. It ensures that there's enough room for variables to allocate it and more. So we're shoving things onto the stack here. We're building up our function. This is known as the function entry. I forget the proper term for it, but there's a sort of dance that happens whenever you start a function that you don't shove everything onto the stack, and then when you end the function, you tear it all down and you give up that memory so that it can be used by other things. So we allocate space on the stack. We'll start looking at the program from the 4th instruction. So we can see that right here. The move $4. We can see that up here as well. We want to analyze the program while it runs, and the best way to do this is by using breakpoints. So we're going to set little points where we can pause within the instructions here, and that allows us to examine the contents of memory so we can see what's actually going on. This can be used, for example, to get passwords out of memory and get past registration programs. So key registration programs, this is one way that you'll see it used in CTF challenges, where you need like a registration code and you can see what it's comparing it against. And what it's comparing against is obviously a known good code. And if you can figure that out, well, you're pretty much set. So breakpoint specifies where the program should stop executing. This is useful as it allows us to look at the state of the program at that particular point. So let's set a breakpoint using the db command, or the command db in this case. And it would be db, and then we have our memory offset here, which is that, again, that move command that we're looking at. So we are going to go ahead and copy that, and conveniently, the memory locations that I have since I'm doing this on the VM are the exact same as our example. So we'll go ahead and grab that, and then start typing, and we'll go ahead and set a breakpoint. So we've got that all set, and when we start running the program, it is going to pause right there, and we can start dumping what's in memory to see what's going on. To ensure the breakpoint is set, we run the PDF at main, so print disassembly function at main. So we're going to see what this is, and we can see that in this column here, we have our breakpoint indicator telling radar 2 that we want to stop it at this point. And yeah, we can see that little B here in the picture as well. Now that we've set a breakpoint, let's run the program using DC. So we can go ahead and type DC, and this is going to start running it. And you can see that it looks like it failed in my specific case. We'll give it a moment. I'm going to go ahead and pause the recording, and I'll play with this just a moment, and then we'll take a look at it again. There we go. It was just being finicky with me. Running that command again, it's just fine. So if we go ahead and do print disassembly function, we can go ahead and see that this memory address is highlighted, indicating that we are sitting at that address at this breakpoint. And we can see running DC will execute the program until we hit a breakpoint, which is what we expect. Once we hit the breakpoint and print out the main function, the RIP, not RIP, there's a difference here, which is the current instruction, shows where execution has stopped. This is the instruction pointer for reference. It shows us, it tells the CPU where we are at in the execution of the flow of code. From the notes above, and this is also worth noting, this is another one of the registers that is provided to us in the CPU. This can be named something differently or different depending on what the memory architecture you are working with is. For 32-bit, this is often referred to as EIP. RIP is the 64-bit version of this. Don't worry too much about that right now. That's just something useful to know, especially if you want to go through and start doing TryHackMes after this, which are little challenges based on this. So RIP, which is the current instruction, shows where execution has stopped. From the notes above, we know that the move instruction is used to transfer values. So we're moving something from the source to the destination. The statement is transferring the value 4, which we can see right over here, into the local CH variable. So we can see that we're moving this into our D word, our double word variable, which is going to be, I believe, if I remember correctly from the top, I don't have these all memorized. It is going to be a 4-byte sized variable, very common to see, and you can see we've got another one there that we're moving the value 4 into. Scroll back down here. To view the contents of the local CH variable, we use the function px at memory address. In this case, the corresponding memory address for local CH will be RB P-0xC, and we can see that at the top where we had our variables defined, so very, very useful to have this here. We'll go ahead, and I'm not going to bother with copying that because we can just type it. We'll do px at, and then RB P dash, or minus 0xC, and we can see that we have a dump of the memory location there. And it looks like we're not seeing 4 here. We'll give it just a second, and I'll go back to it. This instruction prints the values of memory in hex. This shows that the variable currently doesn't have anything stored in it. That's actually because we're paused at it. Once we go past that flow, it's going to save it in that location. Let's execute this instruction and go to the next one using the following command. So which one we goes to the next instruction? This is the step command. So we'll do ds. So DC, just for reference, is continue, which is going to continue the execution flow until we hit a breakpoint. DS is going to step to the next instruction. Now, if we run that and then we do this again, we can see that we have our value saved there. And again, because this is 2 bytes, we can see that it is 2 spaces here. Each one of these is a byte. And we have our variable with a value in it. And we get the following, and we can see that again here. We can see that the first 2 bytes have the value 4. If we do the same process for the next instruction, we'll see that the variable local h, or 8h, has the value 5. So we'll go ahead and do ds. And then we're going to do our memory function. We'll go ahead and scroll up and grab the value of where that's at. So 8h is going to be 0x8. And that is because, again, it is a double word. It's just going to be a little bit after that. And we can see that at that memory location, sure enough, we had the value 5, which is exactly what we expected in this case. If we go to the instruction, move L local 8 to the register EAX, we know from the notes that this moves the value from that variable into the EAX register. To see the value of the EAX register, we can use the command dr, which is going to display the register contents. So if we go ahead and continue on, we'll go ahead and do the PDF at main again to see where we're at and see how many commands we need to go to. And it looks like we need to do 4 more steps so that we have this command run. So we'll do ds, 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 and then ds. And if we do dr, we can see that the contents of EAX, which is going to be the RDX, this is actually half of the register. The E denotes that we're doing 32-bit, which is going to be the lower half of this. These registers can all be split, and that allows for that compatibility between 32-bit, 64-bit, 16-bit, and even lower memory structures. We can see that sure enough, though, at this value, we have the variable set to 4, or the register value set to 4. If we execute the instruction and run the dr command again, we get that the RAX is going to be set to 5. And actually, in this case, it looks like we've skipped over a couple instructions. Where RDX, we have 4, and then this has already been used, RAX, to produce, it looks like, variable C, which is going to be that 9. So we're a little bit ahead, but you can see specifically what we're doing, where we're putting things in registers, using those registers to perform mathematical operations, and then storing it back in variables so that we can reference them. This technically skips the previous instruction, move L local underscore CH EDX, but the same process can be applied to it. And that's where we ended up skipping to, where we had the value 4 chucked in there. This would have been a value 5 beforehand. When we come to the add L EDX EAX, we will know that this will add the values EDX and EAX and store them in EAX, which is what we end up seeing here. And running dr shows us the RAX, which contains 5, and RDX contains 4, so we expect RAX to contain 9 after the instruction is executed. And again, we're just taking things out of folders that, or buckets rather, that happen to be registers, and we are doing math with them. Just very simple addition at this point. Executing ds to move to the next instruction when executing dr, and then executing dr to view the register variable allows us to see that we are correct. So we can see that before this it is 5, and then if we step into the next command, it allows that to run, and we can see that sure enough we end up getting 9. The next few instructions involve moving the values in the registers to the variables and vice versa. And if we do PDF at main again, we can see where that would happen. So we are moving things from our source here into the destination of the variables so that we can actually go back and reference them by the program, which is what we end up doing, or what we end up doing down here. So we can see that sure enough, we have those right here. It looks like those are a little bit cut off for this specific case, but we can see them over here all the same. After that, a string, which is the output, is loaded into a register, and then the printf function is called in the third line. So here we can see we have the call to sim printf. We are zeroing out, it looks like, a couple registers there. However, you can see that sure enough, we're just printing out the value that we would have on the stack at that point. Perfect. So let's go ahead. This is going to make a little bit more sense as we walk through the challenge. So we'll go ahead and do that in just a moment. Let's go ahead and finish up the content that we have for today. So the second line clears the value of EAX, as EAX is sometimes used to store the result from functions. The fourth line clears the value of EAX, and the fifth and sixth lines are used to exit the function. So here we can see this is our little dance that we use to leave everything, and then we're returning back to the previous point in the program that we were calling this from. Again, makes more sense in context, especially when we're looking at a larger program, jumping into a smaller program. Just know that this is just a little dance that you're going to see in every single program. So, cool. To generalize our workflow, the general workflow for working through something like this is, one, we're going to set appropriate breakpoints so that we can set where we want to view things in the code or where we want to pause it so we can step through things. Use DS to move through the instructions and check the values of the register and memory. And if you make a mistake, you can always just reload the program using the OOD command. All right, I'm going to go ahead and pause here. If you want to try this on your own, none of this is very complicated. It's all just using the commands we just covered. However, after the quick break, we're going to go ahead and run through the challenge. All right, we are back. We're going to go ahead and go through the challenge now. So first things first, I've gone ahead and launched Radar 2 in the debug mode, and I've launched the challenge 1 file. This is going to be in the same directory as the actual file 1 was. We can go ahead and start analysis with AA again, and we're going to go ahead and let that finish. I'm going to go ahead and pause this as this took a little while for me before. Once we are back, we'll go ahead and continue on. All right, and we're back with analysis complete. We're going to go ahead and jump to main and see what's going on. Much simpler program this time. So it looks like we have 3 variables that we're going to be looking into and just doing some simple operations with them. So we have main right here, and then we have 3 variables that are being loaded into memory. So we're doing our quick little dance to build up the stack. It looks like we're moving 1 into the double word local char. And I think that might be one of the answers that we have. We'll take a look at that in just a moment. And then we have an 8H variable as well that we're loading 6 into. And let's go ahead and take a quick look at our questions. What is the value of local underscore CH when its corresponding move L construction is called? First, if multiple, so it looks like that is just going to be 1. And then what is the value of EAX when the imul instruction is called? Looks like that's going to be down here. So we're moving the value 1 into EAX, and then we're going to multiply 1 by 6. So the value at there is going to be 6 since we are doing that multiplication there. And then what is the value of local underscore 4H before EAX is set to 0? So we're zeroing it out here, and then it looks like we're taking the value from EAX and then copying it into that other variable we had talked about. And that's going to be pretty easy. That's just going to be 6. So nice and simple. Just to reiterate with that, so we start with our sys main here after we did our analysis, and we can see that we are allocating space for 3 variables. Then we do our nice little stack dance to build up the stack, and we are storing 1 here and then 6 into our other variable, moving one of those into a register so that we can actually evaluate upon it, doing some multiplication, and then storing the result in that multiplication to the variable from the register EAX into the variable local underscore 4H, and then we're just zeroing out EAX to remove any potential for problems. And last but not least, we're tearing back down the stack and returning to the normal flow of command that we would have had beforehand. All right. Hopefully that wasn't too challenging for the first, our nice little first foray into doing reverse engineering. If you have any questions, I'm going to have the TryHackMe Discord linked below. I will also I'm going to have a nice little resource on reverse engineering if you want to dig in further. This is a GitHub repository that I think it has a Gitbook companion that is called Nightmare. It is not necessarily super hard. Nightmare is actually a play on the idea that people think that disassembly is, or reverse engineering rather, can be very, very difficult. Moreover, it's just daunting than anything. So that being said, John will be doing the next video. I will see you guys in a few days. I'll have his channel linked in the video description below. But until then, happy hacking.